Hello, in this video I'd like to derive for you the level field range equation. Our book just calls it the range equation, but I like putting a specifier on it and saying that this only works in situations where something is launched and then returns to the same height. We're going to do a derivation here, and all I mean by that is we're going to do some algebra until something useful happens. It's not immediately obvious. It's not something that you just look at and have an epiphany about. It's something that kind of comes about just from playing with some numbers until something useful happens. So let's set up the situation. First, we've got some projectile, a ball, that's launched at some initial velocity and at some angle above the horizon. We're going to leave it entirely in letters, which I know terrifies a lot of us, but it makes the math a little bit easier. We can just dump in numbers when we do have a specific application. So for right now, we'll just leave it as variables. This projectile, of course, is going to follow a parabolic path, and it's going to be completely symmetric, right? It starts at the same height that it finishes at. The yi has to be equal to the yf. That's the huge condition here. It has to start and finish at the same height. If it does, then we can go about using this useful equation that we get to. So where do we start? I've always taught you that the first thing that we need to do is solve for the time. The time unlocks how far it actually goes. So we'll come back to our very first kinematic equation and say that delta x, the range, is a function of the velocity in x. It's the velocity initial, it's the velocity final in x. There was no acceleration, so it stays the same, just velocity in x, times time. Well, we don't know what that time is. The only way that we've been able to find this time for these big parabolic paths is to go and look at our third kinematic equation, our favorite one because it's the longest. We're going to say that y final equals y initial plus velocity initial in y times time plus 1/2 ay t squared. So now there are two times where we could come back to this zero height. We're going to sub in zero height here. So y final is 0, y initial is 0, and there's VIYT plus 1/2 ay t squared. So the first time is real obvious. When is this thing at a height of 0 meters? Well, when it starts at a time of 0 seconds. The other one isn't quite as obvious. We need to do a little bit of algebra here, and the steps to do it aren't particularly important, but we could find that the other time is actually 2 times the velocity initial in y divided by our acceleration. Again, we're just doing some algebra to solve for t. This is a time that's particularly important to us because we can go back and plug it into the time in the range equation. So let's do that. Let's go ahead and say here that the range, delta x, is a function of the velocity initial in x. But now, not times time, we're going to multiply by another way to say time, this little result that we found down here. So we'll say Vix times 2 VIY divided by acceleration. So here we've just substituted another equation for time. I know that sounds messy, but well, I know where we're going with it, so trust me for now. We could just multiply this together and say that delta x is 2 times Vix times VIY, all that divided by a. Here we're just multiplying again, putting all the terms together. No real scary algebra yet. But this Vix and this VIY are component velocities. And initially all I gave you was Vi, the composite velocity. We could go back to one of the previous videos and find the trig functions that give us those sides, the components, the Vix and the VIY. Well, Vix is the adjacent side, VIY is the opposite side. To find an adjacent side, we'd use the cosine function. So let me start rewriting this now, not with the Vix and the VIY, but with just simply the vi and then the trig function that we use to find that side. So we'll say, instead of vix, it's 2 times, well, the hypotenuse was vi, and then since the x was the adjacent side, we used the cosine function, cosine theta. And then to find viy, again it was the hypotenuse, vi, times the opposite side that we needed. So that was sine of theta. All that still divided by a. Great, this isn't much better. We've still got a ways to go. We don't have it in terms of vix and viy anymore. We have it in terms of things that we knew at the outset, the vi and the angle. Great. But we can now do something nice because we see that there's multiple vi terms in there. We could factor those out. And for the really, really keen trig student, there's a special trig identity here. We see that there's a cosine and a sine together. That can actually be rewritten as something else. And this is what finally gets us to our range equation. We'll say, finally, that delta x equals 2. We've factored out our vi's. We're going to say vi squared, since we saw it twice. And now not times cosine theta times sine theta. That gets rewritten as just sine of 2 theta, all over the acceleration. So this was all just a bunch of algebra magic to find something that's a little bit simpler. We could still do this in 2 or 3 or 4 parts to find the range, or if we are in that one special case where the projectile is returning to the same height that it started from, well, we can just plug in the velocity initial that we know, the angle, and know the acceleration of the planet that we're on, and get the range.